Lecture 28A is about a very important applied topic, especially if you want to be an engineer. We're going to look at forced damped harmonic oscillators again in the case of sinusoidal forcing, either a cosine or sine forcing function, or some combination of them. We'll also look at the very important idea of complexification, where complex numbers and complex functions, Euler's identity, come into play in very interesting and important ways that shed light on what's going on. At the end, we'll look at something called the beating phenomenon for the undamped case, undamped forced harmonic oscillator, when the external forcing frequency as a sinusoidal forcing is close to but not equal to the natural frequency of the oscillator. So here's our basic setup. I am going to go through this in kind of a theoretical way in these slides. Along the way on the board, I'm also going to be thinking about a particular example. So we're thinking about a forced harmonic oscillator. The forcing function you can see is going to be a cosine function. Cosine of omega t, that's an omega, a Greek letter, not a w there. The omega represents what's called the angular frequency of the forcing function. Let me go ahead and pick particular numbers for p, q, and omega for my example on the board here, and I'll just go ahead and use prime notation. I'm going to pick p to be 4, q to be 20, and I'm going to pick omega to be 3. So there's my second order forced ordinary differential equation, harmonic oscillator. I am also, in the simplest kind of case, going to think about an initial condition at rest. In other words, it's at the initial position of 0 when there's no forces acting on it, and initial velocity of 0. We could think about other initial conditions as well, but let's just go ahead and go with this. What do we know so far? We already know that to try to solve something like this, we should consider, first of all, the associated homogeneous equation. Now I'm going to write that on the board, and I'm going to write down the solution for that. It's not going to be on the actual slides themselves. So the associated homogeneous equation is where the right-hand side equals 0, y double prime plus 4y prime plus 20y equals 0. There's no external forcing. This is called non-homogeneous, this is called homogeneous. Another bit of terminology, this is called forced, this is called unforced. We know that we can solve the associated homogeneous equation, find its general solution, and then once we've got that, we can try to guess a particular solution of the original non-homogeneous forced equation and add those two things to get our general solution of the original non-homogeneous forced equation. We also have seen that to guess solutions of this, you'd want to think about the corresponding characteristic polynomial in terms of the eigenvalue lambda. You can think of it either in terms of a system of differential equations, or you can think about it just purely in terms of the second order equation. Convert the y double prime to a lambda squared, convert the y prime to a lambda, and effectively convert the y to a lambda to the 0 power, which is 1. If you try factoring it, you won't really have success. You need the quadratic formula. And you quickly see that because we have a negative number under the square root, we've got complex number eigenvalues. I didn't have to do it that way, but I wanted to. This didn't have to have complex eigenvalues. 16 minus 80 is negative 64. The square root of negative 64 is 8i, where I squared is negative 1. So this becomes an 8i here. Divide everything by 2, I get negative 2 plus or minus 4i. Those are the two eigenvalues for this scalar equation. We can just pick one of them, say e to the negative 2 plus 4i times t to get our complex solution. Expand this out with Euler's formula. E to the I times 4t is cos 4t plus I sine 4t. Multiply the e to the negative 2t through the parentheses. You'll get e to the negative 2t cos 4t plus I e to the negative 2t sine 4t. And when we've done this before, I've really emphasized this is really important. You don't want to stop there. You don't want your answer to have any i's in it. You want to look at the real part of this, y sub re, and the imaginary part that's next to the I, and put those together in a linear combination to get what we've called y sub h, the general solution of the corresponding homogeneous equation, k1 e to the negative 2t cos 4t plus k2 e to the negative 2t sine 4t, no more i's. Okay, we do want a real solution. So again, that's the general solution of the associated homogeneous equation. It's not the general solution of our original forced equation. It's a tool to help us get there. Let's now on the slide go through a more abstract analysis of what's going on with this particular equation and introduce the very important idea of complexification. We're going to consider the associated complexified ODE. Why? Well, that complexified ODE is going to be something that we get the particular solution from. We're going to convert the cosine of an omega t, the forcing function, to e to the I omega t, which by Euler's identity is cos omega t plus I sine omega t. What a weird thing to do. Kind of scratch your head. Why in the world would we want to do that? Well, the first benefit of it is that when we guess a particular solution of this equation, it makes sense to guess an exponential function. And we know ultimately our answer is going to involve cosines and sines. Euler's identity is going to come into play again to get us to our final answer. It's got other benefits too. This complex arithmetic is really, really important. So go ahead and now guess a particular complex valued solution. It's not going to be our final particular solution of the original non-homogeneous equation. It's not going to be our y sub p. We're going to call it y sub c, c for complex, to be some undetermined coefficient, call it little a, times e to the I omega t. Because you've got an e to the I omega t in this complexified equation, it makes sense to guess something like this. This will not be a particular solution with this one, where it's just a cosine. But we will see, because that's a cosine, that ultimately the real part of this will be a particular solution. Okay, though we won't take the time to check that. All right, so just go ahead and do calculus, algebra, in the ordinary way here, keeping in mind that I is the square root of -1, and therefore I squared is -1. Take the derivative of this with respect to t. Because of the chain rule, you're going to get an extra factor of I omega. Here's the first derivative. A I omega e to the I omega t. Take the second derivative, you're going to get another factor of I omega. The omega will be squared, I squared is -1. The I is going to go away, but with a minus sign there for the second derivative. Okay, that's kind of fun. Now let's go ahead and substitute it into this associated complexified ODE, which again is not the same as the one we're interested in the end, but it's going to help us get there. Plug it in to determine what A should be. Find yc double prime plus pyc prime plus qyc. Right here, that's the second derivative. Here's p times the first derivative. And way over here, here's q times the original function. You can factor things out. In every term, there's a factor of a. That can be factored out. There's also a factor of e to the I omega t. That can be factored out. What's left over, one term involves an I, this one right there, times a omega, and also p. And two terms do not involve an I. This one here and this one here. Group together those terms that don't involve an I. Q minus omega squared. Remember, I already factored out the a and the e to the I omega t. It's giving me a q minus omega squared for the real part of this thing inside the parentheses. And then the part that involves the I, what's left over is a p and omega. Put that next to the I right there. The p omega is the imaginary part of that complex number inside the parentheses. Set this equal to the right-hand side and solve for a. In other words, match the coefficients. A times this entire thing needs to equal 1. By the way, if we had not had a 1 coefficient to start with, if it had been, say, 5 in front of the cosine omega t, I would have put a 5 there as well, and there would have been a 5 there. And a would be 5 divided by this entire thing instead of 1 divided by that entire thing. But to keep it simple, let's keep it a 1. Therefore, yeah, here's a. Kind of a messy calculation. Very easy to make a mistake here. Take it step by step. We'll think about it for our example here in a minute. What do? I divide both sides by that expression. So a is 1 divided by that because there's a 1 over there. 1 divided by that expression. 1 divided by this complex number cannot be simplified. Yeah, though it looks less simple when you simplify it. Better to say it cannot be written in terms of a real part and an plus I times an imaginary part. The trick is to multiply the top and the bottom of this fraction by what's called the complex conjugate of the bottom. I've mentioned complex conjugates before. This is a complex number, a real number plus another real number times I. Its complex conjugate would be that same real part minus the previous imaginary part times I. If you do it to the bottom, you've got to do it to the top so that you're really multiplying by a disguised form of 1 here, and you're not changing the value of the expression. When you multiply it out on top, you're multiplying it by 1, so you just get the same thing right there. Like magic, if you multiply it out on the bottom, go ahead and FOIL it out here. First times first, q minus omega squared times itself is q minus omega squared squared. The outside and inside terms from FOILing cancel. Outside times outside is this times negative p omega I. Inside times inside is this times positive p omega I. And these two thises are the same. They cancel. Last times last is p omega I times negative p omega I. Negative p squared omega squared I squared. But I squared is negative 1. So that becomes positive p squared omega squared. All right, cool. And then you can separate this out into two pieces. A real part plus I times an imaginary part. The imaginary part includes the negative sign then, like this. And if I were to write that with shorthand notation, I could write REA, that means real part of A, plus I times the imaginary part of A, which is a real number, as I've emphasized. That thing right there is the real part of A. This thing right here with the negative sign is the imaginary part of A. I could write it as B plus IC for shorthand work. Keep in mind here, since P and Omega and Q are all positive numbers, that C technically is positive here, at least when P is positive. Technically speaking, the damping could be 0, and we will consider that case. Excuse me, C is negative. C is negative because P is positive because of that negative sign. Sorry, that's not showing up very well here. The smartboard gets very strained on me when I get into the lower right corner. Pause the video. You may want to write that down. Keep that in mind. Before I go into the next slide, let's see how this works out with this particular example. So I got the associated homogeneous equation and its general solution down there. Let me erase everything but the general solution of the associated homogeneous equation. With this example, the associated complexified equation is going to have e to the I times 3t on the right-hand side. Because omega is 3, there's a 3t up there. Once again, you guess yc is a, e to the I 3t. So yc prime is going to be 3ia e to the I 3t. And yc double prime is going to be negative 9a e to the I 3t. When you substitute that into the differential equation and set it equal to this thing, you're going to again be able to factor out an a. You're again going to be able to factor out an e to the I times 3t. Set that equal to the right side, e to the I 3t. What goes inside the parentheses? The real part is going to come from yc and yc double prime. Yc gets multiplied by 20. Yc double prime gets multiplied by 1. So I really get 20a and then a minus 9a is 11a, but I've already factored out the a, so I get an 11. And then the imaginary part comes from the derivative times 4, so I get a 12i. 4 times 3 is 12. And this means a is 1 over 11 plus 12i. Multiply that by the complex conjugate, 11 minus 12i, on the top and the bottom. This is going to simplify to 11 minus 12i divided by 11 squared plus 12 squared. That'll be 11 over 121 plus 144 is going to be 265 minus 12 over 265 times I. That's how that works out in our example. Okay? Hang with me here. Lots of important but tricky things to do in this lecture here. Here are some general comments. Well, first let's continue solving for yc. So yc is a e to the I omega t. I'm calling a b plus ic, like I did in the previous slide, though it was also more complicated in terms of p, q, and omega. Times, okay, I use that Euler's identity right there. But this can be multiplied out. I can FOIL this times this. First times first is b cosine omega t. Last times last is going to give you the real part of the real part as well. IC times I times sine omega t is negative c sine omega t because I squared is negative 1. And the part that goes next to the I comes from the outside and inside products, b sine omega t and c cosine omega t. Keep in mind that c here is negative. C is negative, or at least less than or equal to 0 because, again, p was positive, or greater than or equal to 0. Since the original right-hand side forcing function is cosine omega t, it turns out, you're trusting me on this, that to find yp, our particular solution of the original non-homogeneous equation, we take the real part of this thing. If the original right-hand side forcing function was sine omega t, we would take the imaginary part. But it was cosine omega t, we take the real part. That's what goes down there. Go ahead and plug in the values of b and c if you like. B was q minus omega squared over this. C was negative p omega over that, but I have a minus sign there, and the two minuses give you a plus sign. There is our particular solution in terms of p, q, and omega as a function of t time. Very complicated, but it's good. It is good to do it in the general case. Okay, we're going to see it's very good to do it in the general case like this. Here are some general comments. Assuming a general solution, YH, of the associated homogeneous equation, like we found down there, that's our YH, has been found based on eigenvalues. In general, it would be this. A general solution of the homogeneous forced equation, non-homogeneous, excuse me, forced equation, the original equation, is the sum, like I mentioned 10 minutes ago, something like that. YH plus YP. Add the general solution of the homogeneous equation to a particular solution of the non-homogeneous equation. We knew that already, based on the things I've said before. Assuming p is positive in the damped case, we will get that YH goes to 0 as t goes to infinity, which is what you see here because you've got the exponential decay there. And that's going to happen every time you've got damping. We're either going to have in the phase plane, a spiral sink or a real sink. We won't have a center when there's damping. Some important terminology here. In this case, we say the unforced response. The YH is the unforced response because it corresponds to the associated homogeneous equation where there's no external forcing. It is transient. It goes away. That's the terminology used. It goes away. It goes to 0 effectively. And all solutions of all IDPs for this equation, the non-homogeneous equation, the forced one, approach what's called the steady state solution, which is the forced response YP. This thing right here is what every other solution approaches as t goes to infinity. Don't get steady state solution mixed up with equilibrium solution. Equilibrium solutions for us are constant functions that solve differential equations. This is not an equilibrium. This function here is not constant. It oscillates. It's a sinusoid. It's called steady state. It's the long-run behavior. It's also called the forced response. When t is large, we can say y no matter what initial conditions you have, is approximately yp. How good is the approximation? It depends on how big t is and the values of these other things, what the initial conditions are. This is a vague statement, but we're okay with it. All solutions approach the forced response as t gets larger and larger. What does the graph of the forced response look like? It is sinusoidal. We use the word sinusoidal for functions that are cosines, sines, or sums of cosines and sines. Perhaps with a single frequency, perhaps with more than one frequency. I usually keep it to one single frequency when I'm talking about sinusoids. It turns out we can also write it as a, capital A, times cosine of omega t plus phi. This phi is not a function phi like we've used before, it's a number. This is different than we've used phi in this class for before. It's not a function, this is a number. What? We can combine the cosine and sine to get a cosine? It turns out yes. Now I'm not going to explain this in this lecture. I'll say that for lecture 29A to explain where this comes from. I will tell you a little bit about it here. The amplitude, capital A, does equal this. We can relate it to the complex number b plus ci. Well, let's see, what should I erase? This, okay. Let me go ahead and erase this part. For our example, this was b plus ci. So b is 11 over 265 and c is negative 12 over 265. If you plot that complex number in the complex plane, where this is the real axis and this is the imaginary axis, well, for one thing, it'll be very close to the origin. But if I've zoomed in far enough so that I can distinguish it from the origin, it might be right about there. Its real part in absolute value is smaller than its imaginary part, though just barely in absolute value. This would represent 11 over 265 minus 12 over 265i. It turns out the amplitude is the distance between that point and the origin. This distance right there turns out to equal the amplitude of the sinusoid. Equals that. It also, in terms of peak and omega, can be verified to equal this. And it turns out this phase angle in quotes because, well, in here there's no angle. Over here there is an angle. It's this angle. And that, in fact, is why we call it a phase angle, or at least part of the reason. It's that angle, a clockwise angle, which we would consider to be negative typically. It's called the phase angle, and it's got to satisfy this equation. Its tangent is c divided by b, where b is positive and c is negative here, which in terms of peak and omega is this, and you should take the time to verify that. In our example, this one here, p is 4, q is 20, omega is 3. What happens with these numbers? A turns out to be 1 over square root of 265, about 0.06143. 265, is that an accident? No, it's not. That's the amplitude of the sinusoid for our example when p is 4, q is 20, and omega is 3. And the phase angle solved for this equation by taking the inverse tangent, which is okay to do when your number is in the fourth quadrant here of the complex plane. If it were in the other possibility is this third quadrant over to the left here. And then you'd have to actually take the inverse tangent and then subtract pi radians from it. But it's in the fourth quadrant. The inverse tangent will give us an angle in that fourth quadrant. In this case, in terms of radians, it would be about negative 0.83. In terms of degrees, it's about negative 47.5. This angle is about negative 47.5, a negative sign because it's clockwise. Positive angles are counterclockwise. Here's the graph, actually a couple graphs. The pink graph is the graph of the solution of our initial value problem with initial condition y of 0 equals 0 and y prime of 0 is 0. It goes to the origin and it has a slope of 0 at time 0. It's approaching the blue graph. The blue graph is this steady state solution. It's the yp. So blue is yp. and pink is YH plus YP. But YH, the transient, is going away. It's going to 0, so these two graphs approach each other. And that's going to happen no matter what the initial condition is, though if you had a humongous initial condition, it would take longer, of course. And notice that the blue curve does have an amplitude. It looks like of about a little bit bigger than 0.06. How do you interpret the phase angle in this picture? Well, it's close to negative 45 degrees. Positive 45 degrees is 1/8 of a rotation counterclockwise. I guess you'd say negative 45 degrees is 1/8 of a rotation clockwise around a circle. Notice the peak of this blue graph, the first peak, occurs at around, maybe t equals 0.2 to 0.3, somewhere in there. What's the entire period of this blue graph? That horizontal distance is a little bit bigger than 2, it looks like. One period is a little bit bigger than 2 for this blue graph. That distance between 0.2 and 0.3, somewhere along there, is about 1/8 of the entire period. The entire period divided by 8 would be a little bit bigger than 0.25. And what this is representing then, since the cosine function, if you don't add a phi inside there, starts at its peak at time 0, this is representing essentially 1/8 of a period, horizontal translation to the right. That's what it's representing. It is to the right because the phi is actually a negative quantity. It's 1/8, approximately 1/8 of a period. A little bit bigger because this is not exactly negative 45 degrees. It's a little bit bigger than 1/8 of a period of a translation to the right from the regular cosine graph, whose peak starts at t equals 0. So the phase angle can help you understand the horizontal shift. That's the point. All right, for the rest of the class, the rest of this video, we're going to look at the undamped case. The math here gets kind of complicated too. Hang on. More complexification comes into play, more complex numbers. Now let's consider the undamped case, where p is 0, where there's no damping. Of course, that's not realistic. However, if we study the undamped case, maybe we can get some insight into what might happen approximately for the damped case when the damping is very, very small. That's the point of doing this, besides just being more mathematically complete. Again, it's not realistic, but should be a good approximation when the damping is very small. In this case, the unforced response simplifies, so I'm no longer considering this example anymore. I'm considering an undamped case, so p is 0. Y double prime plus some number times y. To make it nice, it'd be nice if it's a perfect square, like 25 or something. Equals cosine omega t for some omega. I could pick omega, but I'm not going to. I'm going to do the general case here again, which gives you the power to think about infinitely many problems all at once. That's the power of thinking about the general case. In this case, the eigenvalues are going to be plus or minus I times square root of q. And if you use Euler's identity to expand the complex solution and take the real and the imaginary parts, they'll just involve cosine and sine and no exponential decays. Cosine square root of q times t and sine square root of q times t are two linearly independent solutions of the associated homogeneous equation. Take a general linear combination of them to get YH. However, unlike the damped case, this thing does not decay to 0 as t increases. So solutions don't approach the forced response. Furthermore, YP simplifies. That work I did before still is valid, but it simplifies to this. In other words, A equals B, and A is not a complex, well, it's not a non-real complex number, it's a real number. Real numbers are complex numbers with 0 imaginary part, but understand what I mean here. And the A, in that complicated formula for A, will end up simplifying to 1 over q minus omega squared. As long as we're not dividing by 0, at least, as long as omega is not plus or minus square root of q. And actually, we're usually considering omega to be positive, so we can usually just say omega is not equal to positive square root of q. Is this right? We should go back a few slides. Just double check quick. Oops, that's the, oh, there we go. Yeah, if p is 0, this term goes away. This part goes away. You get q minus omega squared divided by q minus omega squared squared. One factor of q minus omega cancels. You're left with 1 over q minus omega squared, which is what I have in this slide here. 1 over q minus omega squared. So this forced response is a pure sinusoid again. Cosines are sinusoids. That was confusing to you. But let's solve the IVP. And something extra interesting is going to happen when we do, especially when q is approximately equal to square root of q without actually equaling it. We will see an interesting beating phenomenon. So the general solution of the non-homogeneous equation, you add yh and yp, get this. We'll consider the case where omega does equal square root of q in lecture 29a. We're trying to solve the IVP. Y of 0 is 0, plug in t equals 0, sine of 0 is 0, cosine of 0 is 1. So you get k1 plus 1 over q minus omega squared. Solve for k1, you get negative 1 over q minus omega squared. If you like, you can bring the negative sign into the bottom too. I didn't bother. The derivative is this. Need the chain rule there. Plug in t equals 0 again, set it equal to 0, sine of 0 is 0, so these two terms go away. Cosine of 0 is 1, so you're left with square root of q times k2, which means k2 must be 0, and that's part of what makes this particular IVP nice, is that k2 is 0. So there is one way to write the unique solution of the IVP when p is 0. There's no damping. Okay, it's a generic IVP. I'm not necessarily thinking q is 25. It's just a general q. But I am also thinking about the IVP. Y of 0 and y prime of 0 are both 0. What do the graphs of these look like as q and omega change? Let's use Mathematica to see what's happening to these graphs. This is where it gets extra interesting. Before I show you the Mathematica for those graphs, let me quickly go through some other things in Mathematica related to the stuff I talked about before, the undamped case. These solve value can solve the original forced equation that I considered on the board, where I plugged in p equals 4, q equals 20, and omega equals 3. However, if you do our ordinary expand, it doesn't look very nice. Yikes. You can make it better by also doing trig reduce. Then it looks better. Okay, that would be, I never wrote that answer down, by the way. That would be the unique solution of the IVP when p was 4, q was 20, and omega was 3. If you solved ultimately for the unique solution of the IVP, it's this. And here's where I plotted that function along with the forced response. This thing right there is the forced response. So that forced response again is in blue, and the solution of the IVP is in pink. We can do it for a generic IVP and get this. And I can make a manipulate plot if I like to see that no matter what my initial condition is, no matter what my initial velocity is, and no matter what my initial position is, it'll work still, and Mathematica's stalling on me here. Interesting, it's never stalled in this room before. Let's try boarding that, maybe redoing it or something. I'm not sure. Let me try closing Mathematica and reopening it. Wow, Mathematica stopped working. That's never happened during one of these lectures. See if it works this time. Yes, it's working. So now, no matter what the initial position, no matter what the initial velocity, in the long run, the pink graph approaches the blue graph. The solution of the IVP approaches the force response. That force response comes from the nature of the external forcing function, but in kind of a tricky way. What about this undamped case? There's what the unique solution of the IVP looks like in the undamped case. Based on omega equals 3 and q equals 4. Kind of a weird looking function. Watch what happens as omega gets closer to the square root of q, which is 2 here. Look at that. Isn't that wild? What in the world's going on there? I could pick q to be something else, like, say, 6, and it can happen as well as omega gets close to the square root of 6 in that case, which is 2 something. Weird. What we're seeing here is an example of something called the beating phenomenon. This is most pronounced in real life if you take a tuning fork, or I should say 2 tuning forks, of slightly different frequencies and tap them both. And what you'll hear audibly is the sound waves, the sound, increasing in amplitude, then decreasing, then increasing, then decreasing, over a slow time scale, a long time scale, even though the individual sound waves themselves oscillate very rapidly, have a very high frequency. This slow time scale that you see in there is what's called beating. It's the beating phenomenon. When the oscillation is very large in amplitude, that's a loud sound, and when it's very low, it's a very low sound. We want to try to understand this beating phenomenon now. One way to understand it is just to look at that equation. Why is this happening? Look at this equation and realize that if omega and square root of q are close together, we're essentially adding 2 sinusoids here. We're subtracting there, but that really is the same as adding negative. If these are close but not equal, then I've got these 2 cosine waves that are oscillating at about the same frequency, but slightly off. Sometimes they will be in phase with each other, and sometimes they'll be out of phase. When they're in phase, that's when you tend to get the big oscillations, high sound waves in terms of its amplitude. And when they are out of phase, they cancel essentially, and you get the lower amplitude oscillations. Here's another way to think about this in terms of complex arithmetic. And this next slide or so will be the end of the lecture here. Hang on. I'm going to do some tricky arithmetic here. It's in the book that we use by Blanchard, Devaney, and Hall. It's actually not completely necessary to do this, but I think it's good practice with complex exponentials, and it reinforces that you can derive a lot of trigonometric identities with complex numbers, which is it's a useful thing sometimes. I'm going to do a substitution. I'm going to let alpha equal omega plus square root of q over 2 and beta equal omega minus square root of q over 2, so that alpha plus beta is omega and alpha minus beta is square root of q. That's why I did that, because I'm going to rewrite this complex solution. Well, first of all, as the real part of this, I should say, this particular solution, the unique solution of the IVP, as the real part of a certain complex solution, where the complex solution is this thing right here. And if you think about going backwards, it does make sense. If you think about taking the real part of this, using Euler's identity, this is cosine omega t plus I sine omega t. This thing here would be cosine square root of qt plus I sine square root of qt. If we subtract them, the sine terms go away. Excuse me, they don't go away, but when we take the real part just gives us the cosine terms. This thing is the same as a, so I just called it a. Let's do some slick algebra with this, okay? This is going to seem kind of mysterious, but it's amazing how it works out. Use the substitution here. Replace omega with alpha plus beta. That's the first thing to do. That omega gets replaced with alpha plus beta. Replace square root of q with alpha minus beta. distribute the t and the I through the parentheses to get this times this minus this times this. Why did I do that? Because now this thing inside the parentheses has a common factor of e to the I alpha t in both spots that can be factored out. I'm left with that. Okay, keep going. It's not clear where this is going, but keep going. Use Euler's identity. Replace e to the I beta t with cos beta t plus I sine beta t. Replace e to the negative I beta t with cos negative beta t plus I sine negative beta t. Use the fact that the cosine is an even function. This is the same as cos beta t. And the sine is an odd function. This is the same as negative sine beta t. And what that's going to mean is the sine terms, the cosine terms cancel and the sine terms combine without canceling. Cosine beta t cancels with minus cosine beta t. Two minuses there on the sine makes a plus. These don't cancel. They combine to get 2i sine beta t. 2i sine beta t, but I've also got the a and the e to the I omega t, alpha t, excuse me. Use Euler's identity again, now on this. And also multiply it by I should say. Cosine alpha t times I gives me this. Plus I sine alpha t times I gives me minus sine alpha t. So it's really I times e to the I alpha t that's giving me this. Continue simplifying. Multiply it through. Now take the real part. Remember, our solution function of the IVP is the real part of YC. Now take the real part. We can write our solution function as the real part of YC, which is this, which in terms of omega and square root of 2 is this. What's the purpose of that? Again, by the way, this could have been done without using complex arithmetic. I could have used trigonometric identities to get from here to here. That could have been done. This is now a constant times the product of two sines. Let's think about the frequencies and the periods of these two sines. This is our last slide. Assume that omega is close to square root of q, but not equal to square root of q. Then omega minus square root of q over 2 will be close to 0, but not equal to it. This means the factor sine of omega minus square root of q over 2 times t in the formula from the previous slide at the end has a small frequency because the angular frequency is close to 0. What's the difference between a frequency and an angular frequency? I'll say in a second. That's a slow oscillation. When frequency is high, that's when it's a fast oscillation. When the frequency is low, that's a slower oscillation. That's the beats. Suppose time is in seconds, just to keep things concrete in typical applications. Then the period of this slow oscillation is then what? You should remember from way back in high school, pre-calculus, for a sine function like this, its period would be 2 pi divided by that coefficient of t. 2 pi divided by the absolute value of the coefficient of t. This thing could be a negative coefficient. Take the absolute value. The 2 can go outside of the absolute value and go on top because I'm dividing by it in the bottom and get a 4 pi over the absolute value of omega minus square root of q. That many seconds will be the period of the slow oscillation, and that will be a large number when omega is approximately square root of q. A slow oscillation, a large period. Its frequency is its reciprocal. And if time is in seconds, the frequency would be in hertz. It's really, the angular frequency here is really 2 pi times the regular frequency. The regular frequency has more meaning for most people. It's hertz, that many cycles per second essentially. Hertz is shorthand for 1 over seconds. On the other hand, the other factor is a relatively large frequency and a relatively small period. That was the omega plus square root of q over 2 inside the sine. And its period is 2 pi divided by omega plus square root of q over 2, which can be simplified to this, and I don't need absolute values here because I'm assuming omega is positive and q is positive. The reciprocal of that is the frequency in hertz. That many cycles per unit time. Cycles per second. Let's finish by just looking a little bit more at Mathematica here. Does what we see here match? Omega is 2.2, Q is 5.97. Let's go back to the 4 case. So I changed Q to 4. Square root of Q then is 2. Omega is 2.2. Let me use my calculator to help me here. The period of the slow oscillation, T slow, was 4 pi over the absolute value of omega minus square root of Q. In this case, that's 4 pi divided by the absolute value of 2.2 minus 2, the square root of 4 is Q, which is going to be 0.2. That'll be 20 pi. And 20 pi is approximately 62.8 seconds would be the period of the slow oscillation. And you need to think of the slow oscillation in this picture as, say, starting here, going up, then back down, then back up again. And it's going to get back up again to the low amplitude region close to 62.8. You can't see the whole thing here. That's what would happen. You can see half of it is about 31.4, right about there. It's about half a period of the slow oscillation. You can figure out the period and the frequencies of the fast oscillations as well. I could also figure out the frequency of the slow oscillation. I didn't do that. Take the reciprocal of that. 1 over 62.8 would be a very small frequency, okay? Much smaller than frequency of sound waves. So this is just giving you an idea that this kind of analysis could carry over to, say, sound waves. Thanks for watching.